Let's talk about the chi-square distribution. So the distributions that we've talked about so far in our class include the binomial distribution, which is a discrete probability distribution. We've briefly talked about a uniform distribution, and we've been using the normal distribution and the t-distribution. Here we're looking at another continuous probability distribution called chi-square, and we'll have one more before the end of the semester goes. It's called the f-distribution, and we need chi-square and f to do some very specific hypothesis tests. So for chi-square, unfortunately, chi-square is not like our normal and t-distributions, which are very similar in properties. Chi-square is not symmetric, but as we increase our degrees of freedom, the distribution becomes more symmetric. Here are a couple of graphs. We have a very not symmetric chi-square on the left, and here on the right, we have a chi-square distribution with a degree of freedom of 10 in blue and the degree of freedom 20 in red. And you can see the more degrees of freedom seems to pull it over so that it's starting to look a little more symmetric. Chi-square values can be 0 or positive, but they can never be negative. And chi-square distributions, similar to t's, are different for each number of degrees of freedom depending on the type of test that we're doing. And as we increase degrees of freedom, chi-square approaches a normal distribution. Excel has some built-in functions for chi-square, just as it does for normal and student t-distributions. And these functions are analogous in Google Sheets. So we have chi-square distribution. So the chi-square.dist function returns the probability at a specific test statistic value. So if I wanted to conduct a hypothesis test and I needed a p-value for my test statistic, I would use either chi-square.dist or chi-square.dist.right. So the first one, .dist, is going to return the left side probability of our chi-square distribution. And to draw a quick little graph here, if I had my x value here, the value at which I want to evaluate the distribution, this chi-square dist is going to give me this area for x, but the chi-square dist.rt, meaning right, is going to give me this area to the right. So it will depend on whether we're doing a left-tailed test or a right-tailed test, which one of these functions we'll be using to find that p-value. If I had my significance level and I needed a critical value, if I wanted to run a traditional method hypothesis test, I need to use the chi-square.inverse function, chi-square.inv. In this, we provide the probability and the degrees of freedom, and this function will return the critical value that we need for our hypothesis test. This inverse function, though, returns the left-tailed probability. So if we have a chi-squared distribution here, if my significance level was 0.05 and I had a right-tailed test, I would actually want to enter chi-square.inv 0.95 and those degrees of freedom, because the 0.95 is going to be to the left of that value that I'm looking for. So just be mindful of that. And also, just like all of the other probability distributions we've been talking about, the area under a chi-square distribution is 1. And one more formula for Excel and Google that we'll be looking at is the chi-square.test. In a chi-square.test, the chi-square test returns the test statistic that would be calculated for a goodness of fit test, a test of homogeneity, or a test of independence. So the 3 chi-square tests in chapter 11 would all use this function. All 3 of them have 2 parts: the actual data that's given and the expected data. What are we expecting depending on which test we're doing? Focusing on a goodness of fit test. If I'm trying to determine if something occurs, if some event occurs the same for all 7 days of the week, for example, then my expected range would all be the same number. So I'm looking at a uniform distribution, for example. We'll talk more about how to use this function in those different tests in Chapter 11. Now, before we finish this lesson, let's take a look at working with chi-square. I want to find the critical values of chi-square that determine critical regions containing an area of 0.025 in each tail. So this could likely be a two-tailed test where alpha is 0.05. And we suppose the number of degrees of freedom is 9. So just like any other situation, I like to draw my picture, and chi-squared is a skewed graph, so I'm going to emphasize that skew here. And I'm looking for 0.025 in each tail. And so I'm looking for these two numbers, which I'm going to call x1 and x2. Now I'm going to attempt this in Google Sheets. I want critical values, so I'm going to use the chi-square inverse function, INV, and see that it says it calculates the inverse of the left-tailed chi-square distribution. So when we're doing inverses, we're giving the probabilities and we're finding the x values or the z values. So chi-square.inv, and we'll put in 0.025, degrees of freedom is 9. And it tells me 2.7003, and likely we do 3 decimal places to 2.700. And this is the left, so I'm going to put it on the left side. If I want to do the right, Excel actually has an inverse for the right side, so we could use inv.rt and do the same thing. And apologies that that is not in the table above. I forgot my degrees of freedom. And if we do that, we get 19.0227, and we'd round that to 19.023. But I do want to point out that if we didn't use the right and we wanted to use the left, chi-square.inv, so I'm not going to do the right, but I want to get that same answer of 19.02. We would just type in 1 minus 0.025. So we get that complement. We get everything to the left of that x value, and then we'll still put in 9. And sure enough, we get that same value. So we are able to use the same function to find both of these values, or we use one for the left and one for the right. The key, though, is that chi-square.inv is giving us the x value with the probability to the left. Chi-squared inverse.rt is going to give us the x value with that probability to the right. A couple of things to notice. Both of these values are positive, which for chi-squared, all of our critical values will be positive. Unlike z and t, where the mean is 0, we could have negative values. We do not have that for chi-square. They will all be positive. Next up, we'll talk about how to use chi-squared for some new hypothesis tests.